Good morning, everyone, and we are going to do a short review on how chemistry works in the biology world, all right? And here is our study guide. We're going to start by looking at the periodic table, all right? And the question is, can you find the number of electrons, protons, neutrons, and the atomic weight of certain isotopes? So here we go. Pardon me. Every atom on the periodic table resides in a square on that periodic table. That represents a type of element, okay? And every element, of which the smallest portion is an atom, one atom, is like the human population and one person is one representative of it. We always write these as a capital letter, okay? If it's two letters, the first one is capital and the second one is always lowercase. And here's the reason why. Because we don't want to confuse this with this. This is carbon monoxide, a gas that will kill you. That's cobalt. Okay? So that's why they do that. All right. You'll notice that on this, since we are made of carbon, we're going to start with carbon. But speaking of what we're made out of, we're made of carbons, hydrogens, oxygens, and nitrogens, mostly, all right? So the most important thing is the carbon, all right? We are carbon-based life forms, everything, viruses, bacteria, funguses, trees, people, all right? Well, there's a number in the top corner. What is this little number? This number is called the atomic number. And the atomic number represents two facts, all right? The atomic number is the number of protons, and I write that P with a plus because protons have a positive charge, those particles, and the number of electrons, which we write as an E negative because it's a negative particle, negative charged particle. Now, it says here that carbon is made of 6 positives and 6 negatives. So what is the charge on this? 0. It is neutral. In fact, all the atoms on the periodic table are written that way. Let's look over here. This is why we have only one number in the corner, because that represents the number of protons and the number of electrons for that particular element. Got it? So everything on the periodic table is automatically what we call neutral. 10-4? Okay. Can we change protons? The answer is no. What do I mean by that? Well, if I look over here, calcium has 20 protons. 10-4? What if I took away one proton? If I took away one proton, it becomes potassium. If I had calcium and I added one proton, it becomes scandium, which is named after Scandinavia, by the way. Are you with me? Okay. Hey, I wonder what this one's named after. Francium. France. What about this one? Germanium. Germany. Because if you discover it, you can name it what you want. And a lot of them named it after their home countries. Okay? All right. How are we doing? Good means? Okay. So, don't change your protons. All right. Well, let's take a look. Speaking of protons and electrons, here's a little model that was made by one of my students at Sumter High School many, many moons ago, and I still use it. This is a representation of an atom. This little bundle of blue and clear colored nuggets, this is the nucleus, or the center of the atom. These little nuggets represent the protons and the neutrons, which are the only things that cause any weight. Since atoms are so small, they are counted not as grams, but as AMUs, atomic mass units. Now, how many individual atoms does it take to make 1 gram? 6.02 times 10 to the 23rd, which means a 6 with 23 zeros behind it. That's Avogadro's number. That's how small atoms are. It's amazing, okay? So, 1 AMU and 1 AMU each. Electrons are these little red things going around in these circles. These circles are what we call energy shells, energy levels, quanta, okay? All that means is this is where the moving electrons are, which is why the energy of an atom is in the electrons, because they're the ones that are moving at the speed of light around this nucleus, which is pretty much stationary. Alrighty? Now, I don't want to get into the weeds, but that's me. Is this an accurate representation of the relative sizes? Not at all. If this nucleus were the sun, the closest electrons would be the stars you see in outer space. If this were the nucleus of an electron, the nucleus of an atom, these electrons would be in Greenville. That's way too big to put on a small model. So we put them together. Atoms are 99.999% empty space. It's amazing, okay? All right, well, what's the charge on an electron? Negative. That's on the outside here, okay? Wait a minute. If all the atoms in my hand are 90% empty space and all the atoms on this desk are 90% empty space, how come my hand doesn't go through the desk? Because opposites attract, but likes repel. What's on the outside of every one of these atoms? Negative charges. What's on the outside of every one of these atoms? Negative charges. So they repel each other. That's good news, because otherwise you'd fall through your chair and fall through the floor. 10-4? Okay. So, but I want you to understand, the energy is in these moving electrons. And these guys are not spinning in nice circles. They're spinning around in figure eights, okay, in all sorts of different directions. In fact, they're going so fast, we've never taken a picture of an electron. When you take a picture with the fastest film we have, it looks like a blur. We call that the electron cloud. But if everything was a cloud, how can we possibly count the electrons? So we have to draw it like this, okay? We call this the orbital model. All right, so we now know how to find electrons. We know how to find protons. How do we find neutrons? Well, the neutrons are in here, and they provide the weight of your atom. So, we look at the number at the bottom. The number at the bottom is called the atomic mass. And the atomic mass, my friends, is the average of all the known isotopes. Isotopes. Iso means the same type. Okay? Same type. Well, wait a minute. What you talking about, Willis? Well, let's take a look at two types of carbon. A carbon that weighs 12 and a carbon that weighs 14. 12 AMUs, 14 AMUs. What are the only two particles that have weight or mass? Protons and neutrons. So, we can look over here and we can say, how many protons do I have? Well, it's carbon, so we have 6. Well, how many neutrons do I have? Well, I need to know 6 plus what equals 12, which is the weight. So that would be 6. Okay? And again, we call P plus because it's positive. We call N 0 because it's neutral, no charge. All right? Let's take a look at this one. How many protons do I have? Well, 6. Remember, we cannot change the protons. It doesn't have 7 and 7. All right? Well, if that's the case, I need to get to 14. So how many neutrons do I have? It has to be 8. That is an isotope. That is an isotope. One is lightweight, one is heavier. But they're both what? Types of carbon. Isotope. Same types of atoms. And 4? All right. On my test, part B. On my test, because one of the things I push, whenever you're paying attention to what I'm doing, what are some possible questions we can come up with? The question would be, how many neutrons are in the most abundant isotope of carbon? Well, I've got two isotopes. Gee, who's the most abundant of these two? Well, this 12 or this 14, which one is closer to the average 12.011?
12.
12, okay? And the example I give in my class is like the whole class is taking a quiz of 14 questions, and one person got 14 questions right, everybody else got 12. So what's the average of the class? Exactly 12? No. Exactly 14? No. Somewhere in between? Is it 13? No. It's closer to 12 because there were like 20 kids who made 12. Only one made a 14. So that's why, with this number being so far skewed toward 12, there must be a lot more carbon 12s in the world than carbon 14s in the world. Okay? All right. While we are here, before we go any further, I want to mention that whenever it comes to isotopes, that there are two varieties or more, stable and unstable. This one happens to be the stable type. This one is the unstable type. It is radioactive. Now, when something is radioactive, it doesn't mean it's sending out music like a radio, but it is sending out particles. And those particles radiate out from the center of the nucleus. And this is how it works. Can you slide over here? All right. I'm going to construct a nucleus here. Made up of protons and neutrons. Got it? Your electrons are way out here, and they are not involved. Okay? Well, let's see. I've got 1, 2, 3 neutrons. I've got 1, 2, 3 protons. And so this would be a stable isotope. Usually stable isotopes have generally similar numbers of protons and neutrons in the nucleus. But looky here. I can take neutrons and shovel them in, and all of a sudden, by pushing in neutrons, look at what I'm doing. I'm disrupting what we call the strong force that's holding them together and making the nucleus fly apart. The protons and the neutrons are coming apart. That's radioactivity. And the reason radioactivity is considered dangerous is if these protons or neutrons that are shooting out slam into your DNA, they could knock one of your, adenine and thymine. You could knock these A's and T's and C's and G's out of position, and when your DNA comes back together again, you've now created an incorrect message, which might be cancerous. Okay? Because we don't want to have radioactivity around us. All right? But the cool news is radioactivity is not always our enemy. Like fire is not always our enemy. We use fire to cook. We use fire to keep warm. But if we have a wildfire, that's not good. Okay? Ask people in California. So, can we make radioactive isotopes? Yes. If you're looking at a person's thyroid to see, where the problem is, your thyroid absorbs what? Iodine from the environment. Well, I can make radioactive iodine in a nuclear cyclotron where we spin the iodine around at the speed of light and then introduce a bunch of neutrons and slam into it. And then slowly it breaks apart. Your thyroid will suck up the iodine. We can take a picture and see where the iodine is located. Got it? Same thing, I can make radioactive glucose and see what part of your brain is active. So any part of your body that needs some kind of nutrient, we can make a part of that nutrient radioactive and then count how many radioactive energy bursts we see on a CT scan, for example. Fair enough? Okay. Okay, so that's the difference between those things. So I don't know if we'll have a stable and unstable test question on this particular test, but it will be coming. All right? How are we doing? All right. Let's now talk about how the periodic table is arranged. That's what we're talking about here, with rows and columns and valence electrons and all that kind of good stuff. See that right here? All right. So what I usually do is I hand all of my students a periodic table. You can see it? Okay. And I ask them to do this. Fold the periodic table right behind beryllium. Got it? See how we folded it? All right. And then we're going to fold it again so the beryllium is right next to boron. Right? And then we fold it. You see, I've made a shorter periodic table. What have I done? I've cut out this middle area here called the transition elements, all right? Which are a little bit more complicated than this class demands. So now we have created a shorter periodic table. I have transferred this onto the board. So let's take a quick look. All right. You see, my friends, we've created a shorter periodic table. Instead of 18 columns, it now has 8. And this can now explain what we use the periodic table to do. So, every column we put down. There's 1, this is column 2, column 3, 4, 5, 6, 7, and column 8. Got it? On my test, gee, anybody got a 9th column or a 10th column? No. All right. What does each column represent? Each column, and I'll just bring this over, you keep it. Each column represents how many valence electrons are in this outer shell. You see, my friends, bonding of molecules, bonding of this atom with this atom to form a compound, is all about the valence electrons. Not the ones inside, not the protons, not the neutrons, it's the electrons in the outer shell, the valence electrons. So everybody in column 1 has 1 valence electron. All these have 2, 3, 4, etc. until we get to 8. And the reason we need to stop at 8 is because of something we call the octet rule. I really can't spell. What does that mean? That atoms are happy, they're stable, when they have exactly 8 electrons in their valence shell. The only exception is the first shell. The first shell only holds 2 electrons and then it's full. How do we know that? Because we need to look at these things. These are shells. Got it? Sorry, I apologize. These columns represent the valence electrons, and these rows represent the shells. Like this shell, and this shell, and this shell. Got it? Okay. So, everybody here has 1 shell. Well, who would those guys be? That's hydrogen and helium on your periodic table. And then they're full. Well, wait a minute. 1 electron, 2 electrons, and they're full. See, the first shell is happy with only 2. But look what happens with the 3rd electron. It goes here, then the 4th, 5th, 6th, 7th, 8th, 9th, 10th, because 1, 2, 3, 4, 5, 6, 7, 8 fill that shell. And then 8, and then 8, and then 8. Got it? All right. What are the only atoms on the periodic table that have a full shell and are happy and don't want to bind with anybody else? The last column. We call them the noble gases. Number 1, because they're made of gas. Alrighty? And number 2, just like the nobility back in the old days of kings and queens, the kings and the queens did not associate with the peasants down in the village, neither do any of these atoms. They cannot combine with another atom. Why? Because they've already got their full outer shell. But what does that mean? What's the good news for you and me? Every other atom on the periodic table is not happy being by itself. It needs to combine with something else in order for both of them to end up with full valence shells. Got it? Which is great. That's why we have water and trees and people and rocks and all that kind of stuff. Everything in the universe is made up of atoms that want to combine. Why? Because they got to get to that magic 8 electrons in their valence shell. Okay? All right. Now, how do they do that? They do that by either giving away an electron or taking in an electron. Got it? Giving away or taking in. What? You mean I can't give and take neutrons? Yeah, you can, but neutrons have what charge? So that won't help. And besides, are they in the valence shell? No. Protons, we don't want to change that because it'll change the atom. So the only thing we can change to change charges is the number of electrons. And the only electrons we ever change are in the outer shell. Not the shell under it, or under it, or under it. Always the last shell. All right? And that's why I sometimes ask my students, let's see, this atom here is francium. How many electrons are in its outer shell?
1.
1. And how many, and what shell is that outer shell?
7.
Number 7. See how that works? And, how about calcium? Where's calcium? Calcium's right here. How many electrons are in its outer shell? 2, but what shell is that?
4.
Number 4. See how that works? Just put it together and there you have it. All right? Okay. Now, that tells us how many we have. It doesn't tell me how they work. So that's what we're talking about now. Charges. What's a charge? A plus or a minus. That's a charge. A plus or a minus. How do I go from a plus to a minus? How do I go from a minus to a plus? Well, the only thing I can change are electrons. What's their charge? Minus. Okay? Now, I'm going to put something on my hands, and that might make it easier, but I'll have to clean it up later. If these were negatives, and these are positives, I did it in black, just for you. See it? Okay. If I have 5 positive protons and 5 negative electrons, what's my overall charge?
0.
0. Got it? But what if I give away 1 electron?
Now it's positive 1.
Yeah, see? How about that? 5 pluses and what, only 4 minuses? I'm sorry, I'm covering up my minus. Does that make sense? So I become plus 1. What if I lose 2 negative electrons?
Positive 2.
I'm plus 2 because my pluses are 2 bigger than my minuses. Then 4. And the same thing is true if I were to add fingers. If I had more negatives, remember, I can't change my positives, I can't change my protons. If I add more negative electrons, it'll be negative charge. Fair enough? Okay. So, that's why I'm going to ask you guys to take a different color. And we are now going to look at the valence charge, or sometimes textbooks call it the oxidation number, because this is the number that is used when we oxidize or put elements together. Under the influence of oxygen, that's what I call oxidation. Okay, everybody in column 1 has 1 valence electron. What's the magic number? 8. So is it easier to pull in 7 electrons or get rid of that 1?
Get rid of the 1.
You see, if I get rid of the 1, I'm getting rid of that 1 electron, and I also get rid of the shell. Well, am I stable? Yeah, because guess what's underneath? A full shell of 8. Got it? So even if I lose an electron, I'm still stable because I still have my electrons in a full shell underneath. So if I give away an electron. What's my charge? Plus 1. If I have 2 electrons, easier to give away 2 or pull in 6?
Give away 2.
When I give away 2, everybody in that column is a plus 2. And same thing, plus 3, and here, plus 4. Because we're always giving away an electron to get to the shell underneath. But how about these guys? Well, I've already got 5 negatives, but I got to get to 8. So guess what? I'll take in 3. Well, if I pick up 3 negative electrons, it becomes negative 3. Here, I'm going to pick up 2. I'm going to pick up 1, and guess what? Do I need to pick up or give away anybody? That's why everyone in column number 8 has 0 charge, because we're not giving or taking electrons. Alrighty? What do I need to know? That here we are giving away electrons, and here we are taking in electrons, which is why they become negative. And that's why these become positive. Alright? Now, we can look at this in a reasonable amount by saying, sodium chloride. Okay, where is Mr. Sodium on this periodic table? He's in column number 1. Got it? Here's sodium. Well, what's his charge?
Positive 1.
Plus 1. And where is Mr. Chlorine? Here. And what's chlorine's charge?
Negative 1.
Negative 1. Do opposites attract? That's what holds these together, a positive and a negative ion, okay? But this one gave away 1 electron, and this one took it in. So it works perfectly, okay? Guess what we call this kind of an arrangement? Ionic compound, made of 2 ions. See, this is an ionic compound because it's made of an atom with a plus charge and an atom with a minus charge. Okay, so everybody here has what charge?
Plus 1.
And everybody here has a
Plus 2.
etc., etc. Everybody here has a minus 2, right? Okay. What do I call an atom with a plus charge?
A cation.
Cation. And my students tell me that the T in the middle looks like a plus sign. So that's how we know that's that, okay? So the other kind of ion is an anion, and that's the negative one. Got it? So on my test, if I gave you a bunch of positive and negatively charged atoms, could you tell me which one is the cation and which one is the anion? Yeah. And if the compound is made of this, it's an ionic compound. Okay? Now, one of the things we need to be able to see, where are the metals and the non-metals? Well, let's venture over here to the periodic table on the wall. In class, I would have you take a red pen or pencil, and starting under H, make a series of steps. Got it? Once you finish making those steps, guess what you've just created? The difference between the metals on the left and the non-metals on the right. Okay? So, from here all the way over, including these guys, since they fit right there, are all metals. And only these guys, plus hydrogen, are non-metals. Okay? Now, some non-metals are positive, most of the non-metals are negative, like O and F and Cl and Br. Okay? But why the distinction? Well, metals are solid at room temperature, and they're malleable. You can hit them with a hammer, flatten them out without them breaking, and they conduct electricity. The exact opposite is for the nonmetals. They're gases, so they're not always solids. And if they are solid, you can break them with a hammer, like silicone, which is not silicone plastic, silicon, which is beach sand. You can hit them with a hammer. Is it going to flatten out for you? No. Okay? And it doesn't conduct electricity. All right? Now, the only exception to that rule is that silicon, number 14 up here, since it's right between metal and nonmetal, silicon and germanium, these guys here, are what we call semiconductors. They can conduct electricity, but they don't get hot like a metal wire. That's why we use them to make chips in the computer. Okay? All right, which is really, really cool because are we going to run out of sand to make silicon chips? No. Okay. How we doing? Hanging in there? All right. Okay, tell you what. Let's stop right here and we'll go to the next